Today, we are doing the unconfined compression test. We will be using our lab datasheet, tape measure, sample pan, cohesive soil sample, load cell with our deformation dial gauge, and load dial gauge. The clay sample we are using is remolded Hudson River clay prepared for us by John. We will be loading the sample uniaxially, which is a type of unconsolidated, undrained test where the radial and confining pressure is nominally zero. It's just the atmospheric pressure. And we'll note the value on the load gauge when the deformation gauge reaches certain values. At first, we will start off measuring with high resolution and then proceed to take measurements every 100 dial divisions. These dial divisions correspond to values of deformation and load. One division on the deformation dial corresponds to 1/1000th of an inch vertical deformation. The load dial is interpreted based on a specific chart correlation. We will measure the height and diameter of the sample. We will average the values of 3 measurements because the sample is not completely uniform. We need the diameter to calculate the area for the axial stress and the height to calculate the axial strain. We want the height of the sample to be between 2 and 3 times the diameter in order to prevent overlapping failure planes, which will occur if the sample is too short, or column failure if the sample is too tall. We'll place porous stones on the ends of the sample before placing it in the load cell. This is not necessary, but will allow water to be forced out of the sample more easily, the stress to be distributed more easily, and it keeps the sample from sticking to the load cell. Now, we load the sample in the cell. We can see that there is a gap at the top, so we will jog the machine and raise the lower platform until the sample is just touching the top of the cell. Then, we need to zero the gauges. The deformation gauge has 2 dials. The large one represents the dial divisions that we count to measure the deformation at 1/1000th of an inch per division, and the smaller dial counts how many times the large dial goes around. We will zero the small dial in the deformation gauge, and then zero the large dial. We also want to zero the dial for the load gauge. Here, we can see the correlation is 0.341 pounds per division for the proving ring set up in this load cell. Now, we set the speed of the load cell to around 1 to 2% strain per minute. The bottom will raise at just under 2 millimeters per minute. Now, let's speed this up to about 1,000,000 times faster and watch the sample deform. The test will show the sample failing when the load gauge starts to go backwards as the deformation gauge continues to increase, or when the load gauge stays the same for 3 consecutive readings. We can see the sample bulge in the middle, and we can see the sample cracking. The cracks are the failure planes of the sample. Because this is a clay sample, the strength comes from cohesion, not internal friction, and the failure angle should be close to 45 degrees. Now we will test the values with typical field test methods. Let's cut the sample into even pieces so we can measure the compressive and shear strength of the inside of the sample versus the outer edges of the sample. First, we can look at the compressive strength with the pocket penetrometer. Let's take one of the inside sections. Push the red ring to the base, then insert the tip of the penetrometer up to the red line. This brings the ring to show the value of the compression strength. We will repeat this on the inside of the outer section. You can see the compressive strength is larger here. Now, on the external side of the outer section, we can see that the compressive strength is even larger. This is because the water has been pressed out, so the clay is stiffer. Now let's do the same with the torque vane. This measures the shear strength, not the compressive strength. This can be used in the field, or we can use a larger vane shear test with a torque wrench. We will insert it into the sample all the way, and then twist it while holding the sample until the soil shears and the torque vane spring releases automatically. Then we can see the value here. Doing this on the outside takes a lot more pressure. We then chop up the sample so that John can remold it. We can see the difference between a chunk from the middle and a chunk from the outside. In the field, we would use a drill rig to take a sample of a cohesive soil to measure in the lab. Here, we can see a thin-walled Shelby tube being pushed into the soil by the drill rig. In the back, you can see the hollow stem auger used to drill down to the depth at which the Shelby tube sample is being taken. This is the benefit of a standard drill rig instead of a cone penetration test. We can drill down and take our sample. Then, the sample is carefully extruded from the Shelby tube back at the lab. This column of soil can be tested with a similar procedure we saw today.